Hello, welcome to session number 13 in the series Microwave and Millimeter Wave Circuit Design. I'm Anurag Nigam, and in this section, I'm going to talk about filter designs. And there are different kinds of filters, but I'm going to focus on three. One is the Butterworth filter, another is the Chebyshev filter. I'm not going to talk about inverse Chebyshev, I'm just a Chebyshev filter, and then an elliptic filter. So, uh, there are two methods to design a filter. One is called image impedance method. This results in a constant K or M derived filter. And the theory is that the propagation constant K is a constant, right, in the pass band. And in the stop band, it basically beta is 0. And that means that nothing propagates through the filter. So filter is a frequency selective circuit. It lets certain frequencies through, and that is called the pass band. And there are certain frequencies which don't go through. They are referred to as stop band, right? So we don't use this image impedance method because we doesn't give you much control over attenuation across the stop band or the insertion in the pass band, right? So we use another method which is called insertion loss method. So we are not going to talk about constant K or M derived filters. There are lots of books which you can refer to, right? And the design equations are very simple, right? So you can create any K or M derived filter. But here we are going to talk about we are going to talk about what is called the insertion loss method. In the insertion loss method, what we are trying to do is we have a certain polynomial. For example, we have a maximally flat uh, your Butterworth polynomial, and we do an approximation of that polynomial using a certain number of poles or the order of the filter. So that's the basic idea. So same thing is with the Chebyshev filter also. There's a Chebyshev polynomial, and we do an approximation of that polynomial with a certain number of poles, right? So that's the idea. Elliptic has the same kind of approach, but elliptic is kind of different because in that case, uh, instead of having a closed form representation, I would always have a what is called the approximation of a elliptic. Okay, so I will treat elliptic filter separately. So in this session, I'm going to talk about Butterworth and Chebyshev filters. Now here we can see there are four curves here. Okay, left top basically is a, so I think, okay, so this is plotting attenuation. So attenuation is high in the lower frequencies and it is low in the high frequencies. So this is a high pass filter. Now attenuation is low in the low frequencies while it's high in the high frequencies. That would be called a a low pass filter. So these kind of look reverse to what you are used to seeing. So what you are used to seeing is something reverse, right? So basically you are used to seeing, so what happens is this attenuation is a negative number, right? Okay, so that's why your curves are like that. So if I was to flip them below the axis, right? So if for example I was to do a low pass filter, okay, so now this would be a low pass filter. So that is easier to imagine. So let's do a negative value uh, of attenuation so that you see a familiar response. So this is going to be a low pass filter, right? Similarly, so this is the attenuation. This is a passive circuit, so you cannot go above 0 dB. So this would be called a high pass filter, right? And then I can basically represent a band pass filter like this. So this will be a band pass filter. So attenuation I'm considering to be negative. Okay, and then the band stop filter would look like this. So basically it stops a certain band of frequencies while it lets the adjoining frequencies to pass through. So this would be called a band stop filter. So this is what you are used to seeing. While if you see attenuation as positive, then the previous figures were valid. Okay, so anyways, you understood that If you pass the low frequencies, then it's a low pass. If you pass the high frequencies, then it's going to be a high pass. If you pass a certain band of frequencies, that would be called a band pass. If you stop a certain band of frequencies, that will be called a stop band. Okay, so what is the way of designing? Okay, so I'm going to take the polynomial, and I am going to basically from that extract a certain order of approximation of that polynomial. So that will give me something like the poles, right? And these poles basically they are normalized to a cutoff frequency and an impedance. So I'm assuming that the 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 numbers which I generate would have omega c equal to 1 and z0 equal to 1 ohm. Later you can scale these components to omega c to your choice and the impedance of your choice, which is usually 50 ohm. So once you do a low pass filter, okay, so this is the first thing which I will do, a low pass filter. Then there are certain transformations which can transform a low pass filter into a high pass filter, a low pass filter into a band pass filter, or a band stop filter. So we are going to apply the transformation from low pass to all other kinds of filters, and later we can implement this using physical components which may be distributed or lump components on a LTCC process. So the whole goal is to implement filters on a LTCC process. Okay, now let's go ahead. I'm not going to go into the theory of all this. Okay, I'm rather going to talk about what are the design parameters. So I'm going to use ADS for that purpose, and here I have written the equations. Okay, so I have written some equations for maximally flat or a Butterworth filter. So here this is a zoom in, of this portion. So let's say I at the edge of the frequency, at the edge of the band. So the edge of the band, so I'm plotting it versus omega by omega c. So I'm normalized to 1 minus 1. So the 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 pass band would be less than 0, right? Less than 0 radians per second. So that will be pass band, and more than 0 radians per second, that will be stop band. So let's say at the edge of the pass band, okay, let's say the value is 3 dB. So you can see that the yellow, the line which is blue colored, okay, so this blue colored basically line is representing what I'm expecting at the edge of the frequency of interest, right? And then what I have over here is the order. So here if I change the orders, so let's say this is order 2, right? So the filter response is going to be like this, and at 0, omega by omega c minus 1, at 0 order 2 filter, right, this is going to be 3 dB. So over here if you put a marker, you can read it to be 3 dB. Okay, so at 0, it will be 3 dB roughly here. So this is 3 dB. I don't have a sampling point in between. So this is a 3 dB, correct? Now I can change the order and see its response. So up to 3 dB, nothing is going to change. The corner frequency remains 3 dB. But you will see that the stop band characteristics are changing with the order, right? So now let's say I have a design goal that my stop frequency is twice, or rather this is minus 1, right? Twice. So if I have a frequency twice, it will be equal to omega by omega c is equal to 2 minus 1. That will be 1, right? So let's say if my design goal is twice the frequency, and at this twice frequency I'm looking for a attenuation of let's say 30 dB. Okay, and now I have to decide the order of the filter. So I am going to increase this, and you see at the order of 5 I am achieving 30 dB, right? And this is for a certain corner of minus 3 dB. I can even change this corner. I can change this corner to be 1 dB, correct? So fifth order filter will be not sufficient for that. So in that case, let me raise the order to a higher number. So sixth order filter will do. Now what happens is if you choose the order of the filter to be even number, then on one side you are looking at a termination into 50, and on the other side you are looking at a termination of 1 by 50. So one side you have a resistance, other side you are talking about conductance. So if you want the termination to be symmetric, you choose an odd order filter. So for example, for this same design, okay, where the edge of the band is 1 dB, right, rather than 3 dB, and then you want that the at the twice the frequency it should be better than 30, then you need a seventh order filter. Earlier, you know, people had generated graphs, and using this w by or omega by omega c minus 1, you would figure out the attenuation and then look on those charts, and from that charts you decide the order of the filter. So once you are done with the order of the filter, what you do is you determine the components at omega c equal to 1 and at r equal to r0 equal to 50. Okay, so those components are over here, right? So these are referred to as G0 is 1. If it is odd, G0 is 1, and Gn plus 1. So it is G8 is also 1. And then these are the coefficients in between, right? So these are referring to the components. So you can start with the inductor first, or you can start with the capacitor first, right? So let's look at this representation over here. Okay, so I am looking at capacitor first. So the first component is a capacitor. G1 represents a capacitor, and Gn also represents a capacitor, right? And this is odd order. That's why G0 and Gn plus 1 is going to be your R0 equal to 1, right? So both these numbers G0 and Gn plus 1 would be 1, right? And earlier they used to use tables like this, right? And from this table you would determine the order, right? And then with that order you will go here, look into a table and find out G0, G1 and so on. So G0 is assumed to be 50, while Gn plus 1, so if it is a fifth order, then G6 would be 1. So that means that this is going to be 50 ohm or whatever your normalizing impedance is, right? So G0 and Gn plus 1 is 1, and then the coefficients in between, okay, they can be scaled to result in a low pass structure which looks like so this is stuck. It will be free, it's trying to save it. Yeah, so it is going to be like this: capacitor first, inductor, capacitor, inductor, capacitor. So these are 5 components, and this is a fifth order filter, okay? And then this G0 is 50, and Gn plus 1, which is G6, is also 50. So the terminations are 50 and 50. So that's the advantage of picking up a odd order. If you pick up an even order, then one side will not be 50, it will be 1 over 50, right? So that's the way to do it. Okay, so how do we do it? Okay, I have written some equations, okay, and I can say the specification. Let's say the corner is 30, or sorry, the corner is 3 dB. So this corner is over here, zoomed value. Okay, so at omega by omega c minus 1 equal to 0, this is 3 dB. So there is a 3 dB over here. And then at twice the frequency, okay, at twice the frequency, I'm assuming I will have 40. So I will have 40. So place this line at 40. So this is the 40. That means that the order of the filter can be, okay, so the order of the filter, this line is below. Okay, so we are not meeting this spec. So if you go 7th order, you will meet this spec. So I don't want to do a 7th order. So I will do a 5th order, because you can extend it to any order. It's just that more number of components will be there, right? So let's go with the order. So this would be 5th order with 30, right? And the number which I'm getting is 36 dB. Now I am going to do a 5th order approximation, and these are my coefficients, okay? And these coefficients, if I'm using formula, I can get the table also. Usually, you know, Mathey, Young and Jones has this table given for you. So if you go to my presentation, okay, so here you will see 0.618, 1.618. Okay, so this is 6th order filter, sorry, 5th order. 0.618, 1.618 to 1.618, 0.618. So if you refer to the table, that's that. It's just that I've computed G1 to Gn instead of referring to the table. So you can write these equations and then you can do your own approximation and you will have a fifth order filter. So how do you go about implementing this? Okay. So let us do the following. Okay. I am going to make a new schematic and I am going to call this as uh, LPF is underscore Butterworth. Okay, so LPF Butterworth, create schematic, and I'm doing a fifth order filter. So now I'll write a set of equations. Okay, so in this case I can use a variable, right? And in this variable I will put in G1, G2 and all that. So I have G1, so I'll just type them. So if I look at this one, okay, so I have G1. Okay, come on, let me just minimize this and let me make it small. Okay, fine. So I can see both of them. So G1 is 0.618, 618, right? And so this is delete cut. Okay, G1 is 0.618. G2 is equal to 1.618. Add. G3 is going to be equal to 2. And G4 is going to be symmetric, right? 1.618. And G5, that's the last element, is 0.618. Add. Okay, so these are my coefficients. So accordingly, I will have C1, L2, C3, L4, and C5, right? So let's write the equation for that. So I will do it under variables only. So I'll do another variable, right? So I will say C shunt 1, CSH1 will be equal to, so if I scale this, it will be 1 over omega G1, right? So if you look at my presentation, that is all it's going to be. It is 1 over, so 1 over, oh sorry, G1 over R0 omega C. Okay, so all the capacitances will be of the same format. Okay, G1 divided by that, and all the inductances will be, so R will come in the numerator. So you can refer to David M. Porcher for this, but there should be, so this is a transformation. So I'm not talking. So for this, the capacitance, so let me write it down. Equations. Okay. So let's say CSH1 or C, rather I would say CSH. So CSH, CSH. So this is a shunt capacitor, and the equation is a standard equation. CSH should be equal to GX. Okay, CSH is equal to GX. GX. Okay, divided by, so it will be GX, so divided by bracket Z0. So I will have a Z0, Z0, okay, and omega, okay, omega C. So this omega C, let's say this is omega and this is C, correct? So the shunt capacitors in the low pass filter are going to be this. Okay, so CSHX. Okay, and similarly inductor would be LS. L S x is going to be equal to gx into z0 by omega c. So, this will be multiplied by z0 divided by omega c. Okay, so this is the normal formula which I'm following here, right? So z0 equal to 50, so it will g1 by 50 into omega c, and omega c is basically going to be the frequency for which I'm designing, right? So let's say I want to design for something like 10 gigahertz or 12 gigahertz as a corner frequency, right? So let's do a 12 gigahertz corner frequency, right? So let's go back to our equations. uh, our equations. So in this case, first thing I'm going to put here is omega c, and this omega c is going to be equal to 2 into pi into f naught. F naught is your, or fc. Fc is your corner frequency. Apply. I haven't specified fc, right? So I'll put another variable and I will call this as a fc and z0. So these are my inputs. Fc, let's say, is equal to 12 gigahertz. 12 gigahertz. Okay. And then z naught. Z naught is equal to 50. Okay, so these are my design inputs. This is the order of the filter for a given attenuation of 30 at the twice the frequency. So in this case, that's there. And then this is omega c. Now the next thing which I'm going to write here is LSH, CSH1. CSH1 will be equal to G1, right, divided by omega c into z0. Z0 into omega c, right? Add. So this one I will cut. Okay, so what happened? Okay, cancel that. Write it again. CSH1 is equal to G1 divided by something, which is going to be equal to Z0 into omega c. And I'm going to say add. Then CSH3 will be G3, isn't it? Add. And then you will have CHH5. Okay, so that will be G5, right? Add. And then you have LS2. Okay, so LS2 would be 1 divided by, okay, sorry, it will be G2 multiplied by Z0 divided by omega c, right? So LS2 and LS4 would be equal to G4 into Z0 by omega c. So now we have all these values. Okay, so these values are done. Now I have to put the structure. Okay, the structure would be, okay, let's rotate this, 1, 2 and 3, and we are not going to have any units, so this will be equal to CSH1, this is going to be equal to CSH3, and this is going to be CSH5, right? And then 3, and then you are going to have L. So this is going to be, I'm not going to display R basically is the loss, so this value is going to be LS2. Okay, and the next one would be LS4. Correct. So now we are ready with the low pass filter. right? So we are ready to simulate this. So we will do S parameter simulation, and we have our termination is 50 ohm, right? So that's what we have chosen for this design. Z0 equal to 50. So I'm going to look in the 50 ohm system. Correct? And then I also want to display these values. So I'm going to do the simulation. So I'm designing at 12 gigahertz, right? So at 24 gigahertz, this is going to have an attenuation of 30 dB. So that's what I have chosen, right? So let's put here up to, let's say I go from uh, DC to, let's say, 48 gigahertz, right? Or let's say how much I have plotted, 5 times, right? So it will be 6 times. Okay, 6, 12, 6 is 72, 72, correct? And steps of, let's say, 10 megahertz, it's not going to cry. Okay, that's okay. So that's the simulation which I'm going to do, and then I'll go to the output and I'm going to add CSH1, 3, 5, LS2, LS4. Okay, so that's I'm going to output. And another thing I want to do is there's something called gloop delay, that is d theta by dt. Oh, d, yeah. So that would be the gloop delay. Okay, so we are ready with the simulation. I'm going to simulate this. If I have done something gravely wrong, my result would be wrong. So if I was to plot S21 in dB, that's your filter, right? Now I want to overlay on top of it the response which I got. So first of all, at 24, what do I see? At 24 gigahertz, I see 30 dB. Now I want to overlay on this, or rather I want to overlay on that. So let me go here. This is our standard, right? So I'm going to go here and go to my response, which is under LPF Butterworth. And in this case, I want to look at S21. S21. This is also in dB, right? Okay, hang on. S21 add versus. Uh, I will go to the same LPF and I have the frequency here. Okay, and then I will go here, make this green color, and I want to go to expression. I'm going to plot it versus divided by 12G, right? Divided by 12 gigahertz. So I'm normalizing this to 12G minus 1, isn't it? And say okay. Okay, so this one is green, and this is my circuit design, and this is the approximation of the Butterworth, and I'll make it dotted or short dash. So now you see this is my theoretical, the red one. Red one is theoretical, and the green one is from this circuit, which is a fifth order approximation of that polynomial. So what I'm trying to show you is that mathematics is going to be accurate, right? Mathematics is going to be accurate, and you learn the mathematics, you have more control over the design versus the optimizer. Optimizer is for the very end of your design, not the start of the design, right? So this is the blue one, sorry, the green one is my filter, which is a fifth order filter here, and the red one is my polynomial, fifth order polynomial, right? And they are on top of each other, right? Okay, so you understood what I am trying to do. So the next thing which I'm going to show you is the gloop delay. So So this is my response in gigahertz. And then on top of it, I want to put here the delay to 1 on the right hand side axis. On the right hand side axis. Okay, so now this is something which I want you to see. You would see this delay is from 0 to 7 70 pico, isn't it? 70 picosecond, right? Okay, while it is from this response, okay, let me tell you. In this response, you can see that it is flat, but over a band, you are going to have variation from 40 picosecond to 70 picosecond. This is not flat, right? And this will distort your waveforms. So you understand what I want to do is I want the group delay to be flat and then only rise up wherever there is a corner frequency. So let's see what other filters will do. So before that, I'm going to make all other filters here. Okay, so I want to do a high pass approximation of this, right? So I want to do a high pass. Okay, let's see if I'm recording. Okay, so now I'm going to do a high pass approximation of this low pass. So I'm going to do a transformation of a low pass to high pass. And for that transformation, just look at this. So this is the transformation. Whatever I have as C1, I will divide. So basically, now I have L, okay, which will be LS1 or LSH1 would be 1 over omega square CSH1, right? And CS2 would be equal to 1 over omega square of LS2. So this is a transformation equation. So this is what I'm going to write again, right? These equations I'm going to write for a low pass to high pass transformation. So I'm going to go here into this and I'm going to add another variable, okay, and this variable is going to be the transformation. So I would have compare corresponding to CSH1, I will have LSH1, and this LSH1 would be nothing but 1 over omega square, omega c into omega c or omega c square, right, into CSH1, correct? So this is my LSH1. Similarly, I have LSH3 will be equal to CSH3 here. So this is straightforward. And then LSH5 will be CSH5, right? Add. So now I have done that. Now CS2, right? So if you look at what happens over here, okay, so CS2 is again 1 over omega square L, right? So again 1 over omega square L. So you go here. So CS2 is going to be 1 over omega square LS2, and CS4 would be 1 over omega square LS4, right? Add that. So we are done with the high pass transformation and I'm going to put them here. Okay, so to put them here, I'm going to just copy this one, rotate it out, and this would be my high pass approximation. Copy this one and rotate it out and put it here. Okay, now some designers will be impatient because they already have a background of filter and they say this is going to be too preliminary. Well, we want to take everyone together, right? So you have to bear with me with the preliminary stuff first. Okay, so this is LSH1, then you have LSH2, oh sorry, 3, and then you are going to have LSH5, correct? And you are going to put one more capacitor in between. Sorry. which is going to be CS4. So we have all the equations here, and I'm going to do a 50 ohm on the left and 50 ohm on the right. So we are done. Okay, so 4.3 is my interest, and also I want to go ahead and display an output other set of parameters, which is going to be LSH1, LSH3, LSH5, and CS2 and CS4. Okay, okay, and then I'm going to hit simulate. Okay, so now I'm going to put 4.3. Okay, so I will go here and put 4.3, not delay. Where is the S parameter? Here. So I'm looking at 4.3 in dB. Okay, and that's going to be the high pass. Okay, and I want to put it in the same scale, so I will do this minus 80 to 10. Okay, so x-axis minus 80 to 10. Okay, so again I want to put the same units, right? So it is 10 dB, right? 10. Okay, so I want to just show you what the high pass would be like. Okay, so the corner is around 12. So let's put another marker here. Marker new. So let's look at 3 dB. So 3 dB should be around 12, right? So come on. 3 dB should be around here. Yeah. Yeah, so this is 3 dB. And over here, marker new, 3 dB will be around 12. Yeah, here. Yeah, so 3 dB is around 12. And I am going to do here again delay for 3. Delay for 3. Right, and this I'm going to put on the right hand side axis. Okay, same 40 to 70. Okay, so one is the low pass, the other one is the high pass, correct? And the corner frequency is 12 gigahertz, right? Now I will also put the component values. So I'll go here and I want CSH1, CSH3 and CSH5, and then I want LSH2, LS2 and LS4. So these are the, and I want to look at only one component. So basically, so everyone I will put just one what you call. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12. Okay, so basically it doesn't matter which one because they are just computation, right? Okay, and I will put the equation, this to engineering. Okay, so what do I need? I need 3 shunt capacitors. Okay, okay, so CSH1 is 0.1639, CSH3 is 0.5305, CSH5 is 0.1639, and LS2 is 1.073 nanohenry, and LS4 is 1.073 nanohenry. So that's what the design has been. Next is for the high pass, that after the transformation, we are looking at LSH1 and we are looking at the same value. You will see LSH3, LSH5, right? And then you have got CS2, and then you have got CS4. Okay, so I need 1 nanohenry in shunt, then followed by 0.33 nanohenry, and then 1.073 nanohenry, and then the capacitors are 0.1639 picofarads. Right, so this is my low pass and high pass. Now let's look at the same transformation to band pass. Okay, so if you go here, you would see what did I do. So the G1 is now a resonator, and the resonator values are this. So there is going to be CSH1, LSH1, right? And then you will have CS2, LS2. Then you have CSH3, LSH3, and then you have CS4, LS4, and then you have CSH5, LSH5, right? So this will result in the response. Now I have a choice. I can choose omega 1, omega 2, and then the corner would be 3 dB, right? So I'll choose omega 1, omega 2 to be a number, and then its geometric mean is going to be the center frequency. So let's say I want to design at 10 gigahertz, right? And omega 2 is 12. Omega 2 is 11, and omega 1 is 9. Okay, so for that I'm going to do this design. So what I'm going to do is I'll go to the same equations. Okay, so this is fixed. So I'm going to put here F0. Okay, so F0 is the center frequency. So F0 I'm going to keep as 10 gigahertz, right? And then I have got F2. F2 I want to keep as 11 gigahertz, right? And then I am going to have F1, which is going to be 9 gigahertz. Correct? So this is what I'm going to do. So that would result in delta omega C1, right? So omega C1 will be F1. Okay, F1 add. Then omega C0 is going to be F0 add. Then omega C2 will be equal to F2 add. Then I am going to have delta. Delta would be equal to omega C2 minus omega C1. The whole thing is divided by omega naught, right? So let's see again. The by omega naught. So that is delta. So let's go ahead and write it. Sorry, where did it go? Okay, divided by omega naught. Okay, center frequency, and say add. So now we have delta also. Now I would have to have another convention. So so what I will do is I will add a subscript for band pass as B, right? So what I'm going to have, I'm going to write these equations, okay, in the next one. So this is my inputs, this is my omegas and low pass. This is transformation to high pass. Now I'm going to have transformation to band pass. So I will choose a variable, and in this variable I am interested in LSH1, right? So LSH, I will add a B, it's a band pass, LSHB1, okay, and that value would be equal to, so that value will be equal to G1 over omega 0 R0, sorry, it will be delta into R0, delta into Z0 by omega 0 into G1. So that's what I'm going to write, delta into Z0 by omega 0 into G1. Okay, so this will be delta into Z0 divided by bracket uh, delta into z0 divided by bracket uh, omega naught g1, right? So divided by omega naught into g1. Okay, and say apply. So this is LSH B1. Then LSH B3 will be same thing, just G1 replaced by G3. And then LSB5 will be same thing divided by G5. Okay, the next thing is going to be CSB2. CSB2. Okay, so CSB2 is going to be equal to, or rather CSH. Let's just finish all the shunt elements. CSHB3. Okay, so CSHB3 will be in parallel with, or CSHB1 will be in parallel with LSHB1, right? And that value is G1 over omega 0 R0 delta. So that will be G1 divided by omega 0 Z0 into delta. Correct? So add that. So this will go with LSHB1. Then you will have CSHB3. So it will be G3. And then CSHB5, it will be G5. Okay, and then we are talking about CSB2. Okay, so what is CSB2? Let's have a look. CSB2 is delta over omega 0 R0 G2. It's the same thing, right? Isn't it? Looks similar? No, it is delta over. So it is now flipped, right? So delta over. So let me just go there. So we have to flip that. So this is going to be delta over G2, correct? And say CSB2. Then you will have CSB4. So this will be G4, correct? And then you will have LSB3. And this LSB3 would be G2R0 by delta. G2R0 by omega 0 delta. G2 Z0 divided by omega 0 delta. Correct? So this will be LSB3. Let me just check it once more. G2 R0 omega 0 delta. G2 R0 by omega 0 delta. Similarly, LSB4 will be G4. Okay, so these are my design equation for that. So what I'm going to do here is I'm going to copy this one. Sorry, I'm going to copy this one over here, and this one. So just this component. So this component I'll copy here. Correct. And this is CSHB and LSHB. Right. So this is simple. And then I am going to have this repeated 3 times, right? So this structure will be repeated 3 times. So I'm going to repeat this over here and then repeat it over here. Okay, so in this case I'll make this as 3 and this is 3 and then this is 5 and this is 5. Now, in the practical circuit, what do you expect would be? This looks like an anti-resonator, right? This is the anti-resonant or tank circuit. And then you are going to have a series resonance circuit here. So using resonators, you should be able to implement a band pass filter. Okay, so that's the only insight you have. So you have C here as that. I'm just going to copy this here and this one over here, and I'm going to just move the text over here. And this is going to be CSB2 and LSB2. And I'll just connect this. And similarly, I'm going to just copy these two components and paste them over here. So don't worry, I'll move it slightly. Okay, so this is going to be 4 and this is going to be 4. Okay, so now I'm ready with the band pass filter, and in this case I'm going to put termination as 5 and 6. Correct? So this is 5 and 6 and this, and here I'm going to go ahead and add some more parameters to it. So add, so I want to put CSHB1, CSHB3, CSHB5, LSHB1, LSHB3, LSHB5. Then I'm going to put CSB, CSB2 and CSB4. Then LSB2, LSB2, why there is LSB3? Let me just check it. LSB, CSB2, 4, then LSB2 and LSB, CSB2, CSB4, LSB2 and LSB4. That's correct. Then CSB2, CSB4, LSB2 and LSB4. Okay, so we are done with this, and I'm going to hit simulate. Omega 0. Where did I define omega 0? Oh, this has become omega C0. So this will be omega 0. Sorry. And this will be omega 1. And then there will be omega 2 also, right? Omega 2. F1. 2 pi F1. 2 pi F2. Omega 1 and omega 2. So we have omega 1, omega 2 and omega 0. Okay, so mistake. Okay, undefined omega C1, omega C2 and omega C2 by delta. Okay. Where is the computation of delta? I should change that also. Delta is omega 2 minus omega 1 by omega 0. Okay, now it should be true. Okay, so it's done. Now let's look at the bandpass response. So I have to go and look at 65 dB. 65 dB. Oh, okay, there it is. Okay, I have gone to this frequency. This is for okay for that, but for this one I want to go from, so this is at around 10, right? So I will go from something like, so I'll just zoom it this way so that we are just picking what we want to pick, isn't it? So up to 20 gigahertz, right? So 10, 4, 16. Let's go up to 16 gigahertz. Let's go up to 16 gigahertz. Okay. So this is 11. Okay. So now I'm also going to plot here the delay 6.5 and I want to put this on the right hand side axis. Okay, what happened to my delay? Okay, is there a auto? Yeah. Okay, so again this is that and this is group delay. Okay, somewhere between 40 and that number, right? So even if I want to zoom in further, I can. So let's zoom into this region over here. Okay, so this is my bandpass filter, right? And then the component values, right? So I hate that, but it is repetitive process. Okay, CSHB 1, CSHB 3, CSHB 5, LSB 2, LSB 4, and then I am going to add CSHB 3135. So LSHB 1, LSHB 3, and LSHB 5, and then you have got CSB2, CSB2, CSB4, and LSB2 and LSB4, LSB2 and LSB4, and I would put here, or rather I will just go and put here. Don't worry about this. Come on. So I'll put here 12. So the last one. Okay, let me make sure I'm recording it because sometimes I forget. Okay, 1 hour. Fine. So these are my component values for the band pass filter. And the issue is LSB 2 and 4 are 6.38 nanohenry. 6.438, which is a very large number. Okay, so you understand what this is. We are going to approximate with a line, but again that would be a problem. So we would have to do a, okay, so this is a resonator, right? So we can represent this by a broadside coupling kind of a slot cavity. Okay, so we will see this when we lay it out, so don't worry about it. So this is the band pass filter. Now same thing, I can go ahead and do a band stop filter. So it's just that the resonators will change locations. Okay, anti-resonance would come here and series resonance would come here. So I can create the structure. So but before that, let me write the equations. Okay, so for band stop, these are my transformations. Okay, omega 2, omega 1, and omega naught. Right, these are the same values, so I'm not going to touch that. It's just that these numbers are going to change. Right, so this will be series resonant, that will be the shunt resonant, and that would be the structure like. So let's just do that, right? And after that I am going to do a Chebyshev version of it. Okay, and again there are these curves and I won't have those curves because I have coded these equations, right? So let's go ahead and just do a band stop first. So in the same set of equations, so I will just label them. Okay, so this is going to be insert text. Okay, so this is a equation for low pass. Then this is equation for high pass. Then this is equation for band pass. Correct? So these are equations. Now I'm going to have equation for band stop. So I'll go another variable, and here I will start writing. Okay, so I'm going to have a convention. That convention will be LSH S S1. Okay, so LSH S1 would be Z0 divided by something, which is going to be omega 0 into delta into G1, right? So apply. So this is LSH S1, and LSH S3 will be equal to G3, right? And LSH 5 will be G5. Done. And then you will have CSHS1. Okay, so this is equal to G1 into delta over omega naught Z naught. So this will be G1 into delta divided by omega naught R naught, omega naught Z naught. Okay, so add. This is CSH S1. Then you have S3 will be G3. And then S5 will be G5. Right, and then you will have L. Now you will have a CSS1. Sorry, CSS2. CSS2 would be, so CSS2 is this much. This much, right? CSS2 would be equal to 1 divided by omega naught delta, omega naught into delta into, right, omega naught delta Z0 and G2, Z0 G2, add, and CSS4 will be G4, and say add, and then LSS2 would be G2 delta R0, G2 delta R0. So this number G2 delta LS G2 Z0 delta. So G2 Z0 delta divided by omega naught. Okay, so say add LSS4 will be G4, and say add, and okay, so now my cutoff. Okay, so in the previous figure I forgot to show you this. Okay, let's look at marker new. This is my center frequency, right? So let's go to 9 gigahertz. Should be 3 dB down. Okay, roughly 4 dB down. Marker new. Okay, this is 11 gigahertz. Kind of asymmetric, slightly asymmetric, but that's okay. So that's that it is. This is band pass filter. Now let's look at how would I implement a band stop filter. So I have written the equations for band stop. Control C, Control V. So this is going to be equations for band stop transformation. Okay, so I would create a circuit here. So I will copy these again, Control C, Control V, but instead I am going to connect them in series like this, and they are going to be LSS, LSHS, CSHS, right? Similarly, I can copy this and this would be a parallel combination, right? And copy this. So this would be the parallel combination. This will be LSS and CSS, right? And then I'm going to repeat this. So this would be 3 and 3. And then I'm going to repeat this. This is going to be 4 and this is going to be 4. And then I'm going to repeat this. This is going to be 5 and sorry, this is going to be 5. Okay, so I have shown you all the transformations now, going from low pass to high pass to band pass to band stop. And I have also displayed the component values. Okay, so we are all set. And then I'm going to put here 2 terminals. This is 7 and this is 8. And this is a band stop filter, Butterworth. Okay, this is done. And here I'm going to add those values. So add, I will go to CSHS, this one, add 3, 5. Then I will go to LSS, SHS 1, 3 and 5. Then I will go to CSS, CSS2 and CSS4. And then I will go to LSS2 and LSS4. So we have all those added. Say OK. Say OK. And I'm going to hit simulate. Okay, so I'm going to copy this same design over here, right? And instead of 6, 5, I have got 8, 7, 8 and 7, isn't it? And then delay, I have got 8, 7, 8 and then 7, correct? And then this phase, okay, so that's that. And so this is displayed. And this is at 9 and 11. So slightly off, but it's okay. And then I'm going to represent the values. Okay, so everywhere B will be replaced by S. So let me make sure I'm recording. Sometimes I talk to myself. Okay. So S, 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 okay, so these are my component value for band stop. So I have, let me summarize. I designed a low pass Butterworth, high pass Butterworth, band pass Butterworth, and band stop Butterworth. And these are the component values and these are the simulation response. So this is with the Butterworth filter. Now I want to do a Chebyshev, right? So we'll follow the same lines very quickly. Okay, so to do the Chebyshev, So this is what I did for the Butterworth, right? Let's do this with the Chebyshev. Okay, so go here, and I have written the equations for Chebyshev. Okay, now notice, okay, just notice, okay, uh, this is called ripple. This is a 0.2 dB ripple. So over here, this will be between 0 and 0.2. I have not introduced any insertion loss yet. Okay, so that insertion loss will be on top of this. So I haven't modified my equations for insertion loss. Okay, I'm doing an ideal design right now. And so this basically zooms into this. And I have designed it for a certain ripple at 0, right? Omega by omega c minus 1, 0. At that point, I want it to be 0.2 dB ripple, right? And I want at twice the frequency. Okay, I want, so with a fifth order, I am getting something like 57 dB isolation, right? So do I need a fifth order? Well, the third order will be worse. So this will be fourth order. I won't do fourth order. So I'll do fifth order. So in the fifth order, you will see that the attenuation which I'm going to achieve in Chebyshev is going to be more than what I achieved in Butterworth. But only thing is that I have to allow a certain ripple in the passband. Okay, so this is Chebyshev. Now if this ripple is transferred to the stop band, and this is flat over here, that will be called inverse Chebyshev. So I'm not going to write equation for inverse Chebyshev. You can refer to any book and you'll find those equations. Okay, so my goal is to design this filter which has a 57 dB of stop band at 24 gigahertz, and this is going to be 12 gigahertz, and the ripple is 0.2 dB. So let's go ahead and implement that. Right, so for this I have to write a MATLAB routine. This is the function which will give me the G values. So I want to design for 2, and I want to design for fifth order filter. Right, so I am going to get the G values. So this is 1.3395 and so on, right? So G0 is 1 and Gn plus 1 is 1, and then in between you have this. So let's validate these equations. So quickly go to presentation. Here I'll go to Chebyshev, right? So this one is for a ripple of 0.1 dB, and this is a 0.5 dB ripple. So you would have to find from Mathai, Young and Jones this 0.2 dB ripple, these curves, and then for a certain stop band attenuation you have to figure out the order of the filter, which I do using my equations here. The order of the filter is 5 for 57 dB of stop band, right? Or I can say you have a 40 dB at something like 30, sorry, what is the frequency? It's going to be 1, right? So it's going to be 2. So it would be 2 by omega c minus 1, right? So it will be 40 dB at this point, or 38 dB at this point with this ripple. Okay, so let's do that. So now in this case I have chosen fifth order filter with a stop band at twice the frequency, right? Twice the frequency. Minus 1 is going to be 1. Yeah, over here, correct. So over here I'm expecting 39 dB of rejection at 24 gigahertz with the fifth order. With the seventh order you can cross 40, isn't it? Sixth order and seventh order will be 62. Now you see these ripples, right? If you go up in order, you can see the passband ripples, right? So as you change the order, you can see you will have that many maximas and minimas. So I'll do a fifth order because I don't want to write so much equations. You have already seen the problem, right? So I'll go fifth order. So with this fifth order, let's look at, so I don't have those in here. I would have to refer to Mathai, Young and Jones, or rather I can do one more thing. I can choose let's say 0.5 dB ripple, or let's say 0.1 dB ripple. 0.1 dB ripple. So let's just adjust this. I want to do this for a 0.1 dB ripple. Correct? So LAR is 0.1 dB. So I will achieve in fifth order, I'll achieve 35 dB. So let's say I want to try to achieve 30 dB. So I'm going to achieve 30 dB with 0.1 as a ripple in the fifth order, right? So let's put these numbers and compare it, fifth order numbers. So let's go to its table. So with the 0.1 dB ripple, the fifth order is 1.14. What do I have from MATLAB? Why doesn't it match? Chebyshev 0.1 dB ripple 1319. It doesn't match. Hmm. 13, 133, 133, 14, 13395, 13395. 1337, 13395. I'll have to just hang on a second. Okay, so it seems like I have written some wrong equations in here, and I don't want to carry it further on a Chebyshev till I get my right equations. So what I'll do is I'm going to stop with the Butterworth filter here, right? And in the next session, I will discuss Chebyshev, right? By the time I would have corrected these equations to match the tables from Mathai, right? And then I'll have to just repeat this, which will be just a simple copy. And then in the next session, I will do elliptic. Okay, so I'm gonna stop here because already exceeded 1 hour 17. So I will discuss Chebyshev in the next session. This session was about Butterworth, low pass, high pass, band pass, and band stop. Thanks a lot. Thank you.